Good afternoon, ladies and gentlemen. Good afternoon, ladies and gentlemen. Welcome to the second session on Fischer-Tropsch synthesis. I'm Sara Logdberg from Texas A&M University, and we have a pretty busy schedule this afternoon. 5 papers before the break, and then 3 more after. And first speaker is from the Royal Institute of Technology, Sara Logdberg, and that's joint work with University in Norway, and it's on cobalt particle size effects in Fischer-Tropsch synthesis.
Thank you. Hello everyone. I repeat the title of my work here. It's cobalt particle size effects in alpha and gamma alumina supported catalyst for Fischer-Tropsch. And as the chairman said, this is a collaboration between the Royal Institute of Technology in Stockholm, where I am doing my PhD studies, and also the University in Trondheim in Norway. And these are my co-workers. I want to start to give you a background on my PhD project. It's financed by the Swedish Energy Agency. And the background is the increased interest for carbon dioxide neutral fuels that are made from biomass. And in Sweden we have a lot of pulp and paper industries which produce a rest product which is called black liquor. It's a lignin-rich liquid. And this black liquor can be gasified to produce synthesis gas. And through the Fischer-Tropsch synthesis, we get the so-called green Fischer-Tropsch diesel. And when it's used in cars, it does not contribute to the greenhouse effect. So that's the background. And now to the current study. I want to start to give you some aims when we develop the cobalt Fischer-Tropsch catalyst. We want a high activity from a small amount of cobalt, which means that we want a high dispersion of cobalt on the support. But it's also important when we want to make diesel, we also want a high selectivity to longer hydrocarbons, as you have heard before, or waxes. And in this presentation, I will call this the selectivity to C5+. And we also want to understand what parameters determine the activity and selectivity in Fischer-Tropsch process. I start to show you some earlier results from MTL in Trondheim. I show you the selectivity to C5+ versus the cobalt particle size. And this is for 4 different support materials. The loading is 12%, and it's prepared by conventional incipient weapons impregnation. The different supports are gamma alumina, silica, alpha alumina, and titanium. You can see the trend here. You see an increased selectivity with increased particle size. But if we look closer, we see that when I prepare my catalyst, or when I impregnate the cobalt on the support, the cobalt particle size is actually determined by the pore diameter of the support. So actually the question is, when I see a high selectivity to C5+, is it an effect of the wide pores or the big cobalt particles, or is it an effect of both or of neither? So that's why I made this study. The scope of the work is then to make a closer investigation of cobalt on alpha alumina compared to cobalt on gamma alumina regarding what determines the selectivity to higher hydrocarbons, and also to look at the activity response when I add external water to the reactor under Fischer-Tropsch condition. And I have done this by preparing cobalt on both alpha and gamma alumina support with different cobalt particle sizes and different site densities. So to the experimental part. First I show you the four catalysts supported on alpha alumina. I call them alpha here. And IV stands for incipient wetness impregnation. And 300 is the calcination temperature. So this first IV alpha 300 is 12% cobalt, 0.58% rhenium on alpha. And then I try to sinter the cobalt particles on this support by calcining this catalyst extra in steam at 600 degrees, which I call IV alpha 600. And then I also used another technique to prepare the cobalt phase. It's called a microemulsion. And this catalyst I call Me alpha 300 and Me alpha 600. But due to practical reasons, I could only get a loading of 3.8 weight% of cobalt. And then for the gamma catalyst, the same. I tried to sinter the particles again at 600 degrees. And then I also made two catalysts with a lower loading of cobalt. It's 8 and 6 weight%. But all gamma catalysts are made with impregnation technique. So the Fischer-Tropsch experiments have been performed at a temperature of 210 degrees, a total pressure of 20 bars, and a hydrogen-carbon monoxide ratio of 2.1. And I use 1 to 3 gram of catalyst, which I mix with an inert material. It's a fixed bed reactor. And prior to every Fischer-Tropsch experiment, I have to reduce the catalyst 16 hours in hydrogen. And then I perform the Fischer-Tropsch experiments for 5 days, and it's divided in 5 different periods, A to E. And in the first period, A, I have the same strain gas flow for all catalysts. In period B, I reduce the space velocity of the flow, so I reach a carbon monoxide conversion of 40%. And in period C and D, I add water externally, but I keep the total pressure constant. And in the last period, I shut off the water, so I have dry conditions again. So to the results for the characterization of the catalyst. I start with the pure support materials, alpha and gamma alumina, and you can see that there are significant differences between these two. That's why I chose them. The pore diameter of alpha is much larger than for the gamma, and the surface area is much lower for the alpha catalyst than for the gamma catalyst. And now looking at the cobalt catalyst, you can see here that the degree of reducibility of the cobalt is much higher for all the alpha catalysts than for the gamma catalyst. And here is cobalt dispersion, the total dispersion. And you can see that by using this microemulsion technique, I can actually get a higher dispersion of my cobalt than when I use incipient wetness. And in this column, you see the size of the cobalt particles measured by XRD. And you can see that for the IV alpha catalyst, I have rather large cobalt particles, much larger than for the IV gamma catalyst. But you can also see that I succeeded to make small cobalt particles by using the microemulsion technique here. And then we look at how was it with the sintering, did I succeed with that? And you can see for the alpha catalyst, you see that there is almost no difference or no increase in particle size. So I didn't really succeed with that. And the same is for the gamma. I could see no change in particle size from XRD. But for the microemulsion, I could see an increase when I had this hydrothermal treatment. And here I show that I can achieve different cobalt site densities. And here I mean moles of surface cobalt divided per square meter of the support. And that's also what I wanted to achieve. So the conclusions, fast again. Preparation of cobalt via the microemulsion gives smaller cobalt particles than with the incipient wetness impregnation on alpha alumina. And I also said that it's not possible to increase the cobalt particle size by hydrothermal treatment for the catalyst prepared by impregnation. For the alpha catalyst, the properties were almost unchanged, but for the gamma catalyst, I saw extensive damage upon this treatment. But it's possible to increase or to sinter the particles if the cobalt phase is made by this microemulsion technique. And I achieved a wide range of site densities. And I have excluded this catalyst from my results because it was completely destroyed. So, to the results about the selectivity. Here I show the selectivity to C5+ versus the carbon monoxide conversion. And you see for all the alpha catalyst, the blue-green one you see here, there is a steep increase in selectivity when I increase the conversion. And the increase is not that pronounced for the gamma catalyst. And here it's the same selectivity, but versus the partial pressure of water inside the reactor. And this is only for the alpha catalyst. And you see that the curve looks like this for all the catalysts, irrespectively of this, that these catalysts have much smaller cobalt particle size. You see a steep increase at low partial pressure of water, but then it levels out at higher pressures. And the same curve for the gamma catalyst. You can see that the trend looks the same, but it's not that pronounced as for the alpha catalyst. And then in this diagram I showed you the selectivity again versus the relative site density. It's the surface mole of cobalt per square meter of support area. And here we can see the blue curve is for the alpha catalyst, which have a very low surface area. And it seems like the selectivity is very dependent on the site density. But for the gamma catalyst, I cannot see that relationship. And this is for dry conditions when I have no external water. So I also see that in order for the alpha catalyst to have a higher selectivity than the gamma, they have to have a really high site density. And if I add the cobalt particle size here, you can see that these 2 points are the microemulsion made catalyst. And here, when I increase the particle size from 11 to 18 nanometers, I don't see an increased selectivity. I only see a decrease, which is, I think, due to the lower site density that I obtained. So the conclusion is that I cannot see any cobalt particle size effect on the selectivity from my experiments. We saw that the increased water pressure affects the selectivity to C5+ over the alpha catalyst much more positively than over the gamma catalyst. And I believe that this is a pore size effect and not a cobalt particle size effect. And then we also saw that in order for a alpha catalyst to give higher C5+, selectivity to C5+ than a gamma catalyst, it has to have a really high site densities. So this means, or I propose the theory that the narrow pores that we have in high surface area supports are actually capable of yielding high selectivity to C5+ themselves. And finally, I could not see any particle size effect. So the last results are for the activities and what happens when we add water to the reactor. First, I show you the diagram for the alpha catalyst. Here is the hydrocarbon formation rate versus the final stream. So these are 5 days and the periods that I told you about. A low conversion, and then we decrease the flow to obtain a higher conversion. Then I add water, more water, and then dry conditions again. And on this catalyst, you can see that there is a clear positive effect of adding water here. a moderate amount of water mixed here for all the catalysts, irrespective of the cobalt particle size. And you can also say that I get a positive effect I get an increase in activity when I increase the conversion. And increasing the conversion means also that I increase the partial water pressure. So you can say this is probably also a positive water effect that you see here. And the last picture is the same, but for the gamma catalyst. Here I can only see a positive effect for this catalyst, IV gamma 300, which is 12% loading of cobalt and also some rhenium here. And I see a small positive effect of adding some amount of water. But for the other two with lower loading, I only see the negative effect. So the last slide here. I showed you that I see a clear positive effect at moderate water addition on the activity for all the alpha catalysts. And this is independent or irrespective of the cobalt particle size. But for the gamma catalyst, I see a small positive or small negative effect. It depends on the loading or something else. And with the large difference that we see between the water response for alpha and gamma, that is much higher for the alpha, irrespective of the cobalt particle size, I think this suggests that this is a Port-Sykes effect, and possibly it's non-kinetic. It can be maybe that the large pores in the alpha catalyst are not getting blocked as fast as the smaller pores in the gamma catalyst, with the waxes that are much much longer when I add water. And but I also think that the positive water effect that I observe on both the alpha and gamma catalysts suggests that there is a positive kinetic water effect as well, which has been reported in the literature. And the different magnitudes in response when we add water might be due to the different rate of deactivation, because the water, as we heard earlier, reoxidizes the cobalt particles, and it's easier to reoxidize the small cobalt particles. So maybe that can explain the different magnitudes in the response of added water. So finally, I would just like to thank you for your attention.
Thank you. We have time for questions. Yes.
A quick question about the catalyst prepared using microemulsion method.
Yes.
How do you use cobalt metal with cobalt oxide using a sodium hydroboride?
Sorry, I didn't hear.
Which is to use an agent you use to use cobalt in microemulsion method?
Yeah, I use cobalt chloride as the precursor, and then I reduce it with sodium borohydride.
So I suppose you have some boron in the catalyst.
Yes, I know, I have that.
Can it affect the dependencies we showed about the effect of particle size, so you have some additional chemical composition a little bit different?
Yeah, it could affect the slide I showed you about the importance of site density. So I will actually try to make this point actually. Yeah, this one. I'm not really sure if this is actually it might be an effect of the contamination that I have, but I will also try to make these new points, but with this weapons instead, and see if I get the same trend. But for the other results regarding this, I see the same trend for all these alpha lumens. So I think it's it's a pore size effect, and it doesn't matter for the particle size.
Other questions? Yes,
Are you calculating the C5 plus from the gas analysis, or?
Yes.
if you had excluded the option of cobalt aluminate formation. Gamma.
No, that might be a possible reason that the spinel is formed over the gamma catalyst, and that might be why I cannot see such a high positive effect. That's true.
Short question on that slide. Did you vary the water pressure independently, or is it an effect of increasing conversions?
Yeah, these points are by increasing conversion, and these two are expanding added water.
Okay, thanks.
Okay, thank you very much again.